So, a very good afternoon, everyone. I'm Laksha Chawla, and I'm working at the Intelligent Control Lab in the school. And my advisor is Dr. Yaudiker, and my research topic is multi-view vision models for pedestrian tracking. So, this project is to be deployed for different applications, like where there is like a lot of passengers or a lot of pedestrians, like in the markets or in the airports, etc. So, the agenda of PPT is going to be like this: research summary, the literature review, tools and technologies, methodologies, results, quiz and Q&A, and reviews. So jumping straight to the research focus. Basically, my work is in person re-identification. So in the person re-identification, we are dealing with two different problems, which is one is the re-ID model and the other is re-associations. So I'll just explain, give you an overview of what both of them are. The re-ID, the model, the feature is like the re-ID model, it just AI model which just generates a visual embedding of how a person looks, how distinct a person is from the others in the gallery. And the reassociation, it's actually reassigning the same label to the person. Let's say if the camera is tracking me, if I move out of this room and come back, the camera knows that it's me, Laksha Chawla, yeah. And coming to the problem statement. So basically this kind of system already exists, but what's unique, what novel we are doing is the ReID models. The ReID model should be able to distinguish. My features should be unique from others so that the reassociation could work well. And in dense environment where there are like a lot of cameras, let's say the school, I enter from a gate and I move to some building, like say in the complex building where lighting is a problem, and maybe in 7-Eleven where there are like a lot of collisions, a lot of people, the camera should be able to associate the unique label that yeah, it is me or it is someone XYZ. The proposed architecture says like, okay, proposed architecture is we're using identity associations, we are matching identity associations using cosine distance, and we're using bag of tricks. You cannot play everything by the book, so you need to introduce some tricks actually. So like during the inference, and we are bridging latencies by developing a GPU based pipeline. Everything will be staying on the GPU. If we are relying on the CPU, there are going to be a lot of latencies. Moving further to the literature review, there are some models which are already present. Omni, this OSNet, Omni Scale Feature Learning. So this is a model which was published in 2019. What this model says, it's basically like it is capturing a person's feature from multiple scales, large scale and the small scale, like capturing every distinct information, every discriminative information. And there's a unified aggregation gate which combines all that things. So basically it has a lot of heads which gets combined in the last to form a discriminative feature for every different person. Every different person is going to be a different set of features. And this model, it's actually very, very fast. And it is used in all edge applications. And till now, this has been the baseline, traditional baseline for every re-identification model in the market. And basically, you can see on market 1501, which is the baseline data set for this kind of problems, it has received 94.8 mean average precision with only 2.2 million parameters. That's a really great model. Next is NVIDIA's re-identification net. NVIDIA's re-identification net is NVIDIA's proprietary. It is like a production-ready architecture which you can just plug and play on your applications, NVIDIA-based applications. If your pipeline is on the GPU, you can just plug and play it, and it's going to do everything for you. But that thing doesn't end here. Basically, for re-identification net, you need to scale the associations properly. If you're using like, you need a ReID wrapper and everything, that's what we are doing right now. Basically, re-identification net, it's kind of using ResNet 50 as its backbone. ResNet 50, you can assume it as, in this case, ResNet 50 can be a baseline network. You know, just pull out the softmax layer, the last layer weights. If it's like just 256 neurons, just output those weights, that's your re-identification vector, kind of that. Moving further, we have two frameworks for ReID development. One is Fast ReID, the other is Torch ReID. Fast ReID, both are the frameworks. You can just plug and play your re-identification models, whatever you design. These were published in 2023 and 2019. Torch ReID is more like a traditional research-based alternative, but Fast ReID is for production things. So there are like a lot of state-of-the-art architectures. You can easily swap backbones. You can plug in losses, whatever you like, and with testing with different precisions, like you do in NVIDIA's back-end development, like you can use F float.16 or INT8 according to you. So also we have some state-of-the-art trackers which are using ReID as the basis. Deep sort and bot sort. Deep sort was published in 2017, and deep sort is an ultimate piece of work. It extends sort with some deep appearance features using CNN. Say if two persons are just moving across each other and they happen to have same IOUs, in that case, so that IOUs don't, the global IDs don't exchange each other. In this case, it's deploying a CNN-based alternative so that it can match features. So, and also it is using Kalman filter and hung rate algorithm for linear assignment. Coming to the bot sort, which was published in 2022, it has been a great tracker since then. It is used in many real-world applications. It is introducing improved Kalman filter for tracker detection. Kalman filter was done by deep sort as well, but it's kind of an advanced Kalman filter. They made some changes, and they could not prove it mathematically, but really, it showed significant progress in achieving better accuracy in tracking. And these are the three trackers. The first one is not using ReID. The second and third one are using ReID very successfully. These are the datasets currently in the market. There are like more than 20 datasets. I could not list them all. These are some basic datasets. Market 1501 in the first, and the second Duke MTMC. These are the baselines which everyone are using, and it's like an industry standard. And third is DGNet. DGNet, you just put a database, like just give it a database, and it is using generative adversarial networks (GANs) to make more synthetic images, so that you can achieve better training, you can have some noise, and you can train your ReID model or reassociations better. The other is last. Last is basically this dataset is derived from a movie scene. So same person in different clothes, different locations, different timings. So to just prove your re-identification better. Then comes Wildtrack. Wildtrack is more like for testing your re-identification results. Not exactly re-identification, but bird eye view. From multiple cameras looking at the same person, you need to associate the same person in multiple cameras with the same global ID. So this is our proposed methodology. We just have one design principle, which is data born, modified, and consumed on the GPU itself. It should be like a zero-copy pipeline. Like frames will be decoded, inferred, feature extracted, distant computed, and tracking output all over the GPU. Nothing should go on the CPU. If it goes to the CPU, it's going to use PCIe bus, which is going to introduce a lot of latencies. Moving further, for keeping everything on the GPU, what things we are using, these are the tools and technologies. In the NVIDIA's ecosystem, we are using TensorRT. TensorRT is the basis of every inference in this world, fast inference to be honest. And we are using DeepStream SDK, which is based on a traditional GStreamer, which we used to use before OpenCV. GStreamer, it's a kind of a DeepStream is an advanced version of GStreamer with everything going on over the GPU memory. And CUDA, if you want to introduce some calculations, some new derivations, you need to do it through the CUDA kernels. You need to design a low-level kernel in C or C++ to for all the associations which are to be done over the GPU. And it's really fast. Like you can re-identify more than 200 people in microseconds actually. And these are the hardwares which we have: RTX 5090, 4060 for model training, and for the edge device we have RTX 3060, Jetson Orin, and they have like these GPU architectures: Ampere, Ada Lovelace, and Blackwell. For the development and profiling stack, we're using C and C++ for the final deployments, Python for rapid prototyping and model deployments for training of AI models, and the frameworks are PyTorch, Onyx, Open Neural Network Exchange, TensorRT, and FAS. FAS is Facebook AI Similarity Search. It's a vector database for storing your ReID vectors. That's the proposed methodology. Now we are talking the real thing, what's actually behind this. For inference and metadata. In DeepStream, we have two things, PGIe and STIE. PGI stands for Primary GPU Inference Engine. That's an inference engine. This is kind of your YOLO. YOLO detects people. So this is like detecting people on a large scale, like you can detect more than 200 people in one frame through this NVIDIA's DeepNet model which we have deployed. And the STIE, for every person you have detected, like in this case, if you have detected this person, like this image, this person's image will go to the secondary inference model, which is the SGIE, and the re-identification network will work on this any re-identification net you are using. We are using NVIDIA's re-identification net. If you are using OSNet, that will be working on this particular person's image. And then once we have both the things, we have bounding boxes, confidence, and appearance embeddings, we will register that particular person or that particular target as a tracklet. That's a successful tracklet in our pipeline. We're using bot sort. I told you in the literature review, we're using bot sort, the enhanced version of bot sort. So bot sort is doing some things, which is, okay, these equations. So I'll just quickly explain you, give a summary of how these equations are working. So in the first case, it's a distance scaling using cosine similarity. Cosine similarity, as less the cosine similarity is, as similar the persons having re-identification vectors. If a camera is squaring me, my cosine similarity should be really low with my original tracklet ID. So basically, in this case, so it's calculating cosine distance in this thing, but any constant multiplied by the cosine distance for a particular tracklet. Tracklets are detected by I and detection by J. It's running a nested for loop for that. And combine motion and appearance by calculating a simple weighted sum of appearance cost. This is kind of a combined cost matrix which is being developed at the end, which gets passed to the linear assignment, which is done by the Hungarian algorithm. So there are some improvements which we are making through Hungarian algorithm. It's not as successful always, so we are working on that. And also the reassociation part, which is kind of can be termed as the global registry. Every tracklet which is registered goes to the global registry so that we can monitor every active and lost tracks. Any tracklets which are active in the frame, they are active, and any tracklets which just exited the frame, they are the lost tracks. And we are using Facebook AI similarity search, which is the FAS. FAS was usually used for this LLM and RAG applications, because in LLMs we deal with a lot of vectors, speech vectors. In this case also we are dealing with vectors only, so it can handle the embedding vectors really good over the GPU actually. And the reassociation logic is like, for every track which is currently being tracked, we maintain a rolling window of k-means clustered centroids of that particular embedding vectors. We are clustering them into one centroid and then using that only to match. We cannot keep a long list of vectors that's going to bloat our memory. And the cosine distance, if the cosine distance is less than a particular threshold, for our case it's 0.3, it should be tweaked according to the application, according to the testing site. If the cosine distance is less than 0.3 or the maintained threshold, it's a match, else it's not a match. It's a new ID. A new ID has to be developed in this case. This is a kind of a complete a diagram of how everything is flowing in the pipeline. So this is the testing demo, how basically we are doing testing and everything. So this is a YouTube video. So this we tested outside in the sitting area, I think over that side. I asked some of my lab mates to help me for this. So, okay, let's monitor this girl's GID vectors, which is GID4, and this guy is in the gray sweatshirt, it's GID5. So, my friends will be moving out of the frame. Okay, I'll be coming now. That's me. GID is will be at 6. Yeah. So we'll be moving out of the frame, and let's see how our system re-identifies us. So, okay, my friend, he got a GID5 again. Yep. Me again with the GID6. It re-identified me. GID4, but this guy was re-identified wrong. This ended with GID7, but then got GID10. That's a flaw. And then again, okay, this girl, she entered, she got a GID11. My friend again with the GID5. This girl again with the GID4 with a white jacket. Successfully re-identified. She again got a GID11. So That's all. So that was the testing video of this system. Currently this is in progress. I cannot share with you the exact metrics of how the system is working. Because okay, we need a ground truth for this video so that we'll be able to monitor MOTA scores, which is multi-order tracking accuracy, and HOTA, which is higher order tracking accuracy. We need these, for these metrics, we need a ground truth for this video, which we are working on and allowed. And okay, these are the references for everything, and yes, we can jump to Kahoot.